Alright, so we're still looking at convergence, and we'll start to see what some of the issues are in this lecture. Some good references for this stuff, Weibel, Boardman, and McCleary. Though I'll warn you that one of the things that makes this hard is that there's inconsistent terminology. I mean, one of the things that makes it hard to learn from the literature, and even in reading papers, of course, depending on what source the person was looking at, they might be using inconsistent terminology with the one that you know, and so on. So you really just have to do a deep dive into the spectral sequence that you're looking at in the particular instance. But let's start to investigate some of the issues that come up with convergence. So one of the big issues is, how do you identify the E infinity term? Can you identify it? Can you identify it in a nice way? Can you identify it uniquely? And so on. And so last time, we assumed that we had a bounded spectral sequence. I think we looked at homology and cohomology spectral sequences, but let me just say bounded, and the will work cohomologically for now. So that meant that at each PQ, well, one of the things it told us is that at each PQ, the thing stabilizes at some finite stage. And so that's going to tell us that we look at ERPQ for some large R, and it's going to be isomorphic to ER plus 1 PQ, and the whole point was that this happens at some finite place. And so whatever this value is what we'll call EPQ infinity. And then I think we checked that that agreed with other definitions of EPQ infinity. But one of the first questions we might have is, can we generalize this? Do we need each spot to stabilize, or can we do better? Or sort of have looser conditions, I mean. And another question is, do isomorphic spectral sequences always have isomorphic E infinity terms? So is it possible we land on something else? How do we interpret those results? And so on. Okay. Another big issue that we'll have is reconstructing. Say we even know the E infinity term. How do we then reconstruct the cohomology? So I'm thinking kind of about our example of the cohomology of a space where we had some filtration. We do this for cohomology in the Sayre spectral sequence, in the Bockstein spectral sequence, so whatever cohomology it is that we're interested in. And there are lots of things that could make this hard. So we've already talked about, for example, that we could run into extension problems. So we saw in discussion last time that if we looked at some short exact sequence with Z mod 2 and something in the middle and Z mod 2, that this could show up on the E infinity term of our spectral sequence. And then we see that we don't know necessarily how to resolve this. And in that case, I think we use the universal coefficient theorem to find out this should be a Z mod 4 in the middle rather than Z mod 2 direct sum Z mod 2. Okay, so we might have to solve extension problems, but that's actually really the least of our worries, because things could really be quite a bit worse. So what do I mean by that? Well, last time when we were working with convergence and starting to talk about this, we assumed that we had finite filtrations of our cohomology module, so of each Hn. And the next question is, of course, can we generalize this? We may not always have finite filtrations. In fact, we want to be able to deal with a space that doesn't have a finite filtration. We want to be able to deal with spectra where certainly might not end up with finite filtration. So things could be quite complicated. And then sort of another related question is how unique, or maybe how uniquely determined, are the spectral sequence, kind of as I'm saying above, the filtration quotients, of Hn, so that's like looking at our E infinity term, and also the cohomology. Okay, so these are all kinds of issues that we want to keep in mind, and sort of lots of different aspects of convergence that we might be worried about. Okay, we'll start with essentially the most basic. So maybe let me remind you, I guess we've already started with the most basic. And that's where we had a bounded spectral sequence. So a bounded, let's say, cohomology spectral sequence. But we could do homology here. And we'd say almost the same thing. So it has finitely many non-zero terms. In each total degree. And the upshot of that was this E infinity term stabilizing. So we said at each PQ spot, then eventually, so for some large R, we'll have ER PQ, and we'll look at the differential going out, and it'll be 0. And we'll look at the differential going in, and it'll be 0. And here's where I'm just using this cohomology spectral sequence so I can index it in a particular way. Okay, and that tells us that, maybe let me say for large R. So that tells us that we have this sort of stability, and we can talk about the E infinity term just as whatever this stable value is. Okay, and as an example, we'll always get this kind of situation when we have a first quadrant spectral sequence. And lots of the spectral sequences we've looked at have been first quadrant spectral sequences, or maybe we said, okay, let's just assume that we're in this nice situation so that this particular spectral sequence turns out to be first quadrant. Okay, so that was what it meant to be bounded. And then if we had a bounded thing, we could say that it converges. And maybe I should say, for this, and actually most of this lecture, I'm kind of following Weibel's terminology. I said there's inconsistent terminology. So this bounded spectral sequence converges if for each P plus Q adding to N, there's a finite filtration of our Hn. So maybe it ends in Ft, and that's already 0. We could imagine this continuing on, but all with 0, so we'd name all of those things 0. And then we'll just say Fp plus 1 Hn sits inside Fp Hn, sits inside, and so on. But this does eventually stop. The top thing we'll call Fs Hn. Again, just trying to match Weibel, and then that's Hn at the top. That last one just is Hn. So we need this finite filtration. That's sort of key here. And also identifications of our E infinity terms. So together with isomorphisms, E infinity at the PQ spot should be isomorphic to these filtration quotients. So that'll be Fp Hn mod Fp plus 1 Hn. Okay? And here, of course, S and T may depend on N, so those could vary. Sometimes people write, S is S of n, T is T of n. So I'm not assuming that they all have the same length filtration, but I just need them all to be finite. Okay, so we talked about this last time, and then we went through the example of our cohomology spectral sequence for a finite filtration. So maybe let me say a good exercise at this point. You'll have to go back and remember the homology statement, but it's exactly analogous. So I recommend that you go back and verify that if you have this filtration of some space, and now I want to say that it stops, so that xn is actually x. I think I had a typo in my notes last time. If this is some filtered CW complex, not necessarily the cellular or the CW filtration, but just some cellular filtration, and the point here is that this has a finite filtration, then we get a first quadrant spectral sequence that looks like E1 page is E1PQ. Of course, this is going to be our homology of our relative homology, thinking about the homology of the filtration quotients, and that it converges to HP plus Q of X. So that's saying that there should be some finite filtration and you should identify it. And the identification here, I mean, based on what we did last time, it's just figuring out what do you need to change to make this work for homology. So converging to the homology of X. Okay, so figure out what adjustments you need to make to our argument from last time. Okay, so that's the finite situation. We've basically already talked about that, and yet somehow it takes so long to say. But now we want to start to generalize. What if things are not so finite? Okay, so our next definition, again following Weibel, is that a homology spectral sequence, and now I am going to separate out homology and cohomology just because this is a new concept and because it's easy to get mixed up with inequalities. So we're going to say that a homology spectral sequence is not necessarily bounded, but bounded below if we look at our PQth term on the rth page and it's 0 for all P less than S. And this is for some, I guess really for some R and also for some S, which again might depend on N. Okay, so a good example, and these are the kind of things that typically show up when you start studying more complicated spectral sequences or maybe working in spectra, is a right half plane homology spectral sequence. Okay, so this isn't going to be bounded, but I want to imagine I just have stuff only, non-zero stuff only on the right half plane. And if I look at some spot, well, then eventually my differentials, remember my differentials go to the left and up here for the homology spectral sequence. And so eventually they'll get over into this other side where I have a bunch of zeros. Those should really be the same length, though there's no way I'm going to make them match, so let me stop trying. Okay, so the differentials are eventually 0 going out of this, and Boardman refers to this as exiting differential. So we have this nice result about exiting differentials. We'll come back to that later. But similarly, I could talk about a cohomology spectral sequence being bounded below. And here's really why I'm writing it, because you might think bounded above or something like that. No, I still want to say bounded below. And how do I want to change this? Well, I still want to say that some, on the rth page, some PQ terms vanish. Well, what do I want that to be? I want these to be 0 for all p greater than s. And again, this is really for some r and for some s, which might depend on n. And a good example here is that we could have, say, a left half-plane cohomology spectral sequence. In fact, one way to take a homology spectral sequence and turn it into a cohomology spectral sequence is just to change the signs of the p's and q's, right? So, of course, if I only had things on the right half plane and then I change the signs, I'm going to end up with things on the left half plane. So that is sort of the analogous statement. But now in my cohomology spectral sequence, my differentials go to the right and down. So eventually I will land over here in the vanishing region. But notice that my differentials could come from non-zero stuff really forever if I had completely filled that left half plane. So the point here is really that a bounded below spectral sequence satisfies this condition that we call regular. Okay, so a spectral sequence is regular. And now I'll be kind of lazy and define both at once. Well, it's regular if you look at each spot, as usual, and now what can we say in both of these situations? The whole advantage is that the differentials out of that spot are eventually 0. So the differentials out are eventually all 0, right? Eventually you get to some vanishing region. And certainly we can see that in these special cases of bounded below, say a right half-plane homology spectral sequence or a left half-plane cohomology spectral sequence. Okay, so just to be a little bit more precise, in my cohomology case, let me write my homology case first just to match my notes. So in my homology case, that looks like ERPQ goes to ER something. Of course, we could work out what those indices are, but the point is I want to emphasize that we're going out of the PQ spot. And in the cohomology thing, same deal. So I want to be going out of the PQ spot. And now, of course, my indices over here will be opposite to the negatives of those. But the point is that these are all 0 for some large r. And in fact, for r greater than or equal to some r naught. Okay, maybe a good exercise in playing around with the terminology that we had last time is that this DRPQ, say in the cohomology version, but also in the homology version, you could do the same thing. This is 0 if and only if, when we look at those cocycles, ZRPQ, they stabilize. Now remember, ZRPQ wasn't just the kernel of our differential. We had sort of a funny definition because we wanted these nice successive quotients. And so this is an easy exercise, but it's worth chasing. It's not completely immediate. So what is the point? Regular tells us then that we look at ERPQ and we'll see that it surjects onto ER plus 1 PQ. So think about that as well. And this is for all r greater than or equal to this r naught, wherever this spot has sort of stabilized as in the outward differential, so become all 0. And maybe let me remind you some of that notation we had when we were talking about the infinite cocycles and infinite co-boundaries and whatnot. So let's remember that we had done this for our specific case, I think, but you could define this for any spectral sequence. So ZPQ infinity right? In a sense, all the spectral sequences are the same. So this was the intersection of all those finite stages, co-cycles, and we had our infinite co-boundaries. This was the union of all the co-boundaries from all the pages. And we had this filtration. Basically, we had these nice containments. So B1 PQ was just 0, and that sat inside B2 PQ, and so on. And then the union was this B infinity PQ. And then that sat inside Z PQ infinity. And that was the intersection of all of these ZRs, and they were all nested too. So that lived inside Z2 PQ, for example, which is inside Z1 PQ. And this was where we started our spectral sequence. We let that be E1 PQ. Okay, I guess in a general spectral sequence, you don't have to start on the E1 page, but we could make similar definitions, so it's not so bad. With that, we had ER PQ. This was the co-cycles mod the co-boundaries. And now we had to do some work to identify that really as the co-homology of the previous page, right? So that's not just kernel mod image on the face of it, though it will turn out to be isomorphic to that. And so what am I trying to say? Well, after you've done this exercise and you think about what happens for a regular spectral sequence, where all the differentials coming out at each spot are eventually 0, well, we can still define, of course, this EPQ infinity. Doesn't show up on any of the pages necessarily, but it's ZPQ infinity mod BPQ infinity, okay? And the whole point is that when we're regular, well, we've just seen the z's stabilize, so ZPQ infinity is really ZPQR for all large R. Okay, and so anyway, we have kind of a better understanding of this E infinity term, but it's not something that has stabilized at some finite stage. We still have to mod out by B infinity, and B infinity could really mean that we need to just take the union of all of these things, right? That it doesn't stop at some finite time. Okay, so then Weibull defines, using all of this terminology, I don't really mean here that this definition is due to Weibull, but I just mean that I'm following Weibull when I use this terminology. He says that a spectral sequence weakly converges when, so I guess I'm just going to do co-homology spectral sequence and not specify, but it doesn't really matter. You could just change the indices for homology spectral sequence. So I'll say it weakly converges to some sort of co-homology, hopefully that we're interested in. If you look at each HN, and this has a filtration that looks like not necessarily a finite filtration, but we've got this sort of nested filtered pieces. Okay, so this is some filtration of our R module HN, and there are some identified isomorphisms with our E infinity term. So now this might not show up on any finite page, even for a given PQ, but we somehow have isomorphisms identifying it with HN. I was about to say H, so I wrote it. Mod FP plus 1 HN, so with each of these successive filtration quotients. And then he points out that you should notice that this why do we say weakly converges? Well, we're going to miss out on some stuff. So one thing is that the spectral sequence cannot detect any elements of the intersection of all the filtration quotients. Sorry, of all the filtered pieces. Ooh, okay, so if I had something that was in the intersection of all of them, then it would end up dying in each of these filtration quotients, and so I just wouldn't even see it here on the E infinity page, right? And I also can't detect elements of Hn that aren't in the union of these filtered pieces. Okay, that sort of, to me, seems weird, but of course, just because I have this sequence of filtered pieces, do I really know that I get all of Hn, sort of in some sense, eventually when I take this union? Not necessarily. So, okay, the moral of the story is we basically want to ignore the situation where there's anything in this difference. We're going to want the union to actually be the Hn that we're after, otherwise it's not very helpful. And so then he says a spectral sequence abuts, and you'll see this terminology a lot. I think he also uses the word approaches, but I think I see more commonly abuts to the cohomology if it weakly converges. So we've got filtrations and identifications of those filtration quotients with our E infinity terms. And what do we need? Well, maybe let me say and also, because there are going to be two things. Well, we should rule out these funny situations. So let's make Hn be the union. If you were filtering something else, then throw that thing away and just filter the union. And also, this intersection that we wouldn't be able to see, let's hope that that's 0. So this should be for all n. Okay, so sometimes people just say abuts to the E infinity page, and they don't really specify that we have these conditions, so tend to think that we have these conditions in mind. Again, I'm following Weibel's terminology here. It's not consistent everywhere. But so the whole point is that we have this spectral sequence. There's a filtration of each of these things that we're after, and we've identified the E infinity terms with those filtration quotients, and we're not missing anything in terms of things that are in the intersection of all these filtrations, filtered pieces, or things that don't show up in the union of them. And then he says, well, really, why are we specifying this? It's really that every weakly convergent spectral sequence, once you've identified those E infinity terms, it abuts to, and so that's why sometimes people just say the E infinity term. Well, all you can really get is the union mod the intersection. Okay, so whatever you thought you were converging to, or whatever you thought the abutment was, it's really this. Okay, and then with that, he can say when a spectral sequence converges. And so a spectral sequence converges to some cohomology if it abuts to the cohomology. So we've got this union condition and the intersection is 0. We want it to be regular, so we don't necessarily have stabilization of each of those E infinity terms in the sense that we can't see it at any finite page necessarily, but we do have that all the differentials going out at each spot are 0, and so we have at least surjectivity from one term to the next eventually. And what's the last thing that we need? We want, just trying to emphasize the and, not define the and. So the last thing that we need is that Hn is the inverse limit of Hn mod its filtered pieces. Okay, and again, that should be true for all n. Okay, so we'll have to investigate this in more detail, but the upshot here that we should take away, at least for the moment, is that if a spectral sequence is bounded, then we've got a good situation. And even if it's bounded below and abuts to some cohomology, meaning we've got this good union and intersection property, then it actually converges. To the cohomology. And why is that? Well, this last, so bounded below, we said, meant that the thing was regular, right? And if it abuts to the cohomology, then we've got some filtration where we've identified the E infinity terms as the isomorphic to these filtration quotients. Okay, the fact that it abuts means that we also have this good condition on the union and the intersection of the filtration. And then the last piece is that for this thing to converge, we need this inverse limit condition. But if we have our spectral sequence bounded below, remember that even at the rth page for large R, our EPQ terms will vanish for certain p degrees, and so that's going to give us that this inverse limit that this inverse limit condition is satisfied automatically. All right, so we'll investigate this more deeply in the next video.